So today we are going to start with the magnetic effects of current. Okay. Now when you talk about the magnetic fields, first of all you need to understand we have already discussed field before, and I have told you that field is the modified space, right? Like in case of charges, the modified space around a charge was called as an electric field, right? Now when you talk about magnets, okay, there is a modified space, and that modified space is called as the magnetic field. Fine. Now there was a guy by the name Hans Christian Ørsted. Okay, Hans Christian Ørsted. In 1820, very important thing, a very important milestone in the history of science. This guy used to carry a magnetic needle in his pocket of the coat, and while performing experiments with the circuits, electrical circuits, so there was an electrical circuit, for example this, it has a battery, it has a key, and was something like this, okay? The positive terminal of the battery, the negative terminal of the battery, and this bulb pen. So while performing experiments, what happened was the pocket in which his he had kept the magnetic needle for 20 years in his pocket because he was trying to understand how does the magnetic field of Earth change with time. Okay? This was something that he was working on. But on this day in 1820, he was not doing anything with the magnetic fields. What he was doing, he was working with an electrical circuit. And what he did was, he took out the compass which was in his pocket because it was not letting him work properly. So he took it out and placed it on the table on which this electrical circuit was placed. And the moment he kept the electrical needle here, this was the North Pole, this was the South Pole, and he connected the key. When the key was connected, the bulb started to glow. This needle here started to deflect. This needle, this is a magnetic needle. This needle started to deflect either here or here. And he was amazed to see, because there was nothing which can be termed as the magnetic field which has the tendency to deflect this needle. This magnetic needle can only be deflected once there is what? A proper magnetic field, isn't it? But he could not understand why this magnetic needle is deflecting, irrespective of the fact that the only thing which was present, which was very close to this magnetic needle, was this electrical circuit. That's it. And from this experiment he came to the conclusion that when current flows in the circuits, the current was flowing like this, right? So when current flows in the circuits, what he realized was, when current is flowing in conductors, these conductors have the tendency to generate magnetic fields. So the concept of magnetic fields was not only limited to a bar magnet or a horseshoe magnet. Electric field is purely generated by charges, but from today onwards, remember this thing. Magnetic fields, yes, it is generated by magnets. It is generated by magnets, and along with that, you must remember, it can be generated by current carrying conductors. Current carrying conductors. They have the tendency to generate the magnetic fields as well. Is that fine? So magnetic field can be generated by magnets, magnetic field can be generated by current carrying conductors. So this was something which he was not doing, and he came up with this discovery in 1820. And this is the reason we have the magnetic effects of current. Clear? And what he also observed was, when he reversed the polarity of this battery here, when the polarity was reversed, so if this was positive and this was negative, okay, and what he realized was the deflection here changed. If it was towards right in the beginning, it was towards left in the second side. And what he came up with a rule called as the swimmer's rule. Okay, this was the concept. So I will not discuss the swimmer, so I'll directly come to the concept of how and where, what is the actual rule to understand the direction of the magnetic fields. Is it clear? Is there any doubt in this? Then, first of all, we need to understand how does a magnet, as I've already discussed in electromagnetic induction, what is the general way of representing the magnetic field around a magnet. So here we have a magnet, a bar magnet, okay. In this bar magnet, you know, we have two poles, one is the north and the other is what? The south, right? But remember, this pole, north pole, is not actually the north. It is the south pole in reality. Why? This north is the north seeking pole, because earth, you know, it is also a magnet, right? This north is directed towards the earth, towards the earth's magnetic south. We call this as north seeking pole. What? North seeking pole. And this is what? The south seeking pole. This is not south pole and north pole. Better is to say north seeking pole, and this is called as the south seeking pole. Is that fine? Now, the magnetic field lines, as we already know, they arise from the north pole, okay, and they terminate at, yes, the south pole, okay. And you see the magnetic field lines are closed curves. They are closed curves. Why? Because yes, from the outside of the magnet, they come from north and terminate at south. But when you talk about the interior of the magnet, in the inside, the magnetic field lines run from south to north. Is that clear? Hence, they form what? Closed loops. So the magnetic field lines are closed loops. Closed loops confirms the fact that a magnetic monopole cannot exist. What is magnetic monopole? For example, someone tells you there is a north pole. It's not possible to have an isolated north pole. Because whenever there is north, there will always be its south. Is that fine? What is the reason? The reason is these magnetic field lines are closed. When they are closed, they always have to be in close association with the other pole, so they always have to be there. You can only close them, you can only form their loops when you have north as well as south. When there is a single pole, is it possible? No, it's not, right? Fine. So whenever we talk about the magnetic field lines, they always start from north, they terminate at south, but inside they are continuous from south to north, and therefore they form closed loops. One important deduction is we cannot have isolated poles. Isolated magnetic poles do not exist. They do not exist. Is this clear? Okay. Some other property. The magnetic field lines are packed closer near the poles. Now see, the density of these field lines is much higher at the poles as compared to in between, right? Can you tell me what you conclude from this fact? I have taught you in the previous class. What can we conclude from this? The density is more at the poles and less at the other regions. What do we conclude from this? I talked about flux in the previous class, if you remember. I told you flux is the number of field lines crossing your area. So here the flux is higher as compared to the flux here. More number of field lines means more strength of the magnetic field. So it means the magnetic field has higher strength when it is very close to the poles. The magnetic field is less strong, or it has less strength here. So if you compare region 1 with region 2, if I ask you where do we have more magnetic field? So the magnetic field is more at 1 and less at 2. Is that fine? Is this clear? This is the concept. Third point, the closer the magnetic field line, the stronger the magnetic field. Okay, again the same thing. If the magnetic field is lines are very close here, so that means the strength of the magnetic field is more. If the lines are very far away from each other, it means the strength of the magnetic field is less. Is that fine? And very important thing, the magnetic field lines do not cross each other. They do not cross, they do not intersect. Can anyone tell me the reason? I have told it already. I have told it already in electromagnetic Faraday's lab, if you remember. Why don't they cross each other? You have written it. They don't cross each other because if they cross, then we will have multiple directions of the magnetic field at a point. Is that fine? And therefore, it is not possible for them to intersect. So actually, if someone tells me, what is the direction of magnetic field here? The direction of magnetic field is the tangent. What is the direction of magnetic field at this point? The direction of magnetic field at this point is the direction of the tangent. This is the direction, okay? But if they cross, now if the lines cross, say for example there is a point where the lines cross, and I ask you, what is the direction of the magnetic field at this point? You again have to draw the tangent, right? But at this point now you will be drawing two tangents. One will be here and the other one will be here. So you will be confused about the direction, isn't it? Therefore, it is not possible for the magnetic field lines to cross. Is this clear? This is the concept of the magnetic field lines which are generated around a permanent magnet. Clear? Fine? Copy this. And some important information about the magnets that I want to share with you. Now, this end and this end are at some length, right? Let this be Lg, the geometrical length of the magnet, okay? Fine? This is the geometrical length, fine? But the north and the south pole are not at the edges. They are always somewhere a little inside, okay? Somewhere here and somewhere here. Fine? So this length up from this point up till this point, this is called as the magnetic length, okay? And this magnetic length is lesser than the geometrical length. And you must remember that the magnetic length is 5/7 times the geometrical length. That is, the original length of the magnet is much longer as compared to the magnetic length, because the pole to pole distance is less as compared to edge distance. Is that fine? Okay, this is the reality of the magnets. Fine?
Yes, sir.
The length of the magnets is geometrical length, okay? But the poles are not at the edges, they are a little inside, okay? So the length is 5/7 times that of the original length. Fine? Okay. Should I go to the next page? Okay. Done? Okay. Now after this comes a very important concept. Now, as per Hans Christian Ørsted, you already know that whenever current is flowing in conductors, it also generates magnetic field, isn't it? The year was 1820, right? When Hans Christian Ørsted came up with the concept that when current flows in conductors, it generates magnetic field. Do you know? In 1821, in 1820 only. In 1820 only. When Hans Christian Ørsted told the world that guys, when current flows in conductors, magnetic field is generated, there were two scientists. One was Biot and the other one was Savart. Jean Baptiste Biot and Felix Savart. In 1820 only, these two come up with a way to find the magnitude of the magnetic field, which is due to the current carrying conductors. So as per them, they gave a law called as the Biot-Savart law. Okay? And as per this law, if there is a current carrying conductor, for example this, current is flowing I, okay? And due to this current carrying conductor, now you know there is magnetic field, right? If you want to calculate the magnetic field, say at point P, which is at a distance of R, okay? Fine? Felix Biot and Savart, they came up with the law. The law was this: if you want to calculate the magnetic field at point P, then the equation is this: small magnetic field dB, it is equal to mu naught I dl sine of theta upon 4 pi r squared. This is the law. This is the equation. This is the original method to find the magnetic field. Mu naught is the coefficient of permeability. If you remember, I have told you in the concept of electromagnetic induction as well. Mu naught has a value of 4 pi into 10 to the power -7 Tesla meter per ampere. Okay? Yeah, Tesla is the unit of magnetic field. This magnetic field is measured in Teslas, okay? It is not only the cars in Dubai. dl is a small element here, so I'm taking a small element here, okay, and the angle that it makes is theta. Fine. So this is the angle, the current, that element dl, and r is the distance. R is the distance. So let me not name this as r, or let me just remove this. Yeah, this is it. So the current carrying conductor, the current that is flowing is I. The distance that I have taken for the small element is r. It is at an angle of theta. Then dB is calculated by this. But this is a small magnetic field. So whenever you have to calculate the total magnetic field, you have to integrate this expression. Okay. dB. D is differential magnetic field, small magnetic field due to this small element. But this current carrying conductor consists of several such elements, right? So what you have to do, whenever you have to find the total, you have to integrate this expression. Integrate means you have to use this sign. Is it fine? Mu naught I dl sine of theta divided by 4 pi r squared. I is the current flowing in the conductor. So this is the magnitude. Now if you want to find the direction, very important. If you want to find the direction, what is the method of finding the direction? Yes, Tagli? How do you find the direction of the magnetic field at point P? No idea? See, for this you have to come up with a right hand thumb rule. Very important. Look at me. Don't use your mobile phones, okay? So whenever you have to find the direction of the magnetic field, the right hand thumb rule comes to your rescue. Now what is this rule? As per this rule, stretch your right hand in such a way that the thumb points along the direction of the current. Thumb points along the direction of the... So in this case, current is like this, right? The thumb has to be along the direction of the current. Then what you have to do is, you have to curl your fingers towards the point of analysis. The point of analysis is here, right? So we have to find the magnetic field at point P. So what do you do? Curl your fingers. Curl means if the current was like this, when you start to curl your fingers are going into the board because you are going towards point P, right? Point P is on the right. Is it clear? So current is flowing up. So if you want to curl your fingers are going like this. So that means the magnetic field at point P is inwards, and whenever you show inwards magnetic field, remember it is a vector, therefore you can show it by cross. So the magnetic field on this side is cross. Why is it cross? The reason is, do you know how do you represent a vector? If you remember, I have told you, vector can be shown by arrows, right? So if you are shooting an arrow, what will you see when you shoot an arrow? You'll see the back side, right? And it is a cross. So when your magnetic field is going in, you will see the cross of the arrows. That is why it is cross. Is this fine? And if the point was here, if you are asked to find the direction of the magnetic field at point Q, how do you find it? Use your right hand again. The thumb will go along the direction of the current. Now you have to curl your fingers towards Q. So when you curl your fingers towards Q, see what is happening? The fingers are coming out, right? That means the magnetic field at point Q is, yes, outwards. Is that fine? Outwards means when your arrow is coming towards you. So what will you see? You will see a dot, right? When someone is shooting an arrow towards you, what will you see? Will you see the cross or the dot? You will see the dot, right? So you can represent this magnetic field in the form of dots. Is this clear? So DL is the small length here. Is the direction of the magnetic fields clear? So how do you find the direction of the magnetic fields? Okay? Tell me what is the direction of the magnetic field? Come on. At point P. Yes? Hamda? Tell me, what is the direction of the magnetic field at point P? Maliha? Tell me the direction of the magnetic field at point P. Rauda squad, both of you are asked to find the direction. Fatima Talal, and you as well. Alia, tell me the direction. The words? How?
I'm just guessing.
Yes, Tagir? No? Try it out. You just use your right hand thumb rule.
I told you when you asked me, I told you
I don't listen to you. So what you are supposed to do? Again, I am asking you to understand that concept. The concept is you have to use your right hand and use your thumb in such a way that your thumb points along the direction of the current. And then curl the fingers towards the point of analysis. So if the current is flowing like this, the fingers are going into the board, isn't it? Right? So when they are going into the board, that means you can show it by cross, and you can say that it is inwards. Khalas. Now tell me, what is the direction of the magnetic field? Come on. At both the points P and Q, but the current is flowing down. Yes. Try it out. Yeah. Yeah, good.
Q outward.
Q is outwards.
And
P is inwards. See what you have to do. Right? The fingers are going in at point P. Isn't it? So that means this is cross. And now at point Q, again the same thing, but then when you do like this, they are coming out from point Q. So that means here it is up. Here it is out. Is that fine? What is the direction of the magnetic field at Q? Come on, tell me. See, like this, Outwards. Is this clear? You have to try, because once you try, you will understand how to use. Again, telling you one thing. I had one of my students in Nadal Shiva. What she used to do? She used to rotate her hand like this. The natural curling of her hands is through the palm. Okay, it's not against the palm. She would go like, she would be like, sir, okay, if this is like this, for this we go like this. No, it's not like that. You do not rotate it against your what is this? The free twist, okay? The free joint movement is this. But when you go like this is against the natural movement, right? This is not allowed. You are allowed to use your right hand in such a way that it goes towards your own heart. Fine? The direction has to be like that. Is this clear? Okay, now if I give you some more examples, tell me the direction of the magnetic fields. So we have point P, point Q. Point P, point Q. Point P is here for this case, okay? Now tell me what is the direction of the magnetic fields in each and every case. I'll ask from Hamza, tell me. For the first case, what is the direction of the magnetic field for point P? Point P inwards. How? The current, the thumb along the direction of current, and then your hand is going in. So correct, it is inwards. Hint, look at me. What is the direction of magnetic field for point Q? Outwards. How? So again you use the right hand, okay? So your current is going like this. So for point Q, the fingers are coming out. So when they are coming out, you can show them by dots. Is that fine? Clear? Okay, Tadreeb. What about the magnetic field at point P? At point P, is it outwards? How? The current is flowing like this, and you will go like this, right? Remember, the right hand rule is only used for the conventional direction of current. That is the direction of the positive charges. Here, electrons are moving. Is that fine? If electrons are going like this, so that means your current is flowing like this. Very important. Like for example, I have this electrical circuit, for example. Okay, this is the voltage, so this is the positive terminal, this is the negative terminal. So for us, when we show current, we show it from positive to negative, right? But in reality, the protons don't move. What moves? The electrons, right? And the electrons in this case are moving like this, see? The electrons are moving like this. From the negative towards the positive. So remember, conventional current is this is the actual current. But the right hand rule is only used for conventional current. That means the motion of the positive charges. Here I have shown electrons to be moving from left to right. Therefore you have to change it to the concept of the positive charges. That means the positive charges will be flowing like this in reverse order. That means if you want to find the direction of the magnetic field at point P, how you use it? Current is flowing like this. At point P it will be inwards. And at point Q it will be outwards. Is this clear? Or if the electron is given, electrons are moving, you find the direction with the help of electronic current and then change it. So for electronic current, point P was outwards, right? Change it to cross. Why? Because this is not the actual, the conventional current. This is the electronic current. Is that fine? Now, what about this case? Current is flowing I. What about the magnetic field at point P? Yes? For point P, in this case. We cannot, right? So current is flowing like this. So this point lies along the axis of the current. Remember, at point P there is no electric field, no magnetic field. Because You can use this to curl it here or here. It will not be, if the conductor is going like this, so this point lies on the conductor, there is no magnetic field. Is this clear? Turn off the AC. Turn off the AC. Is this clear? Okay? Okay, now I come to a very important point. Now the first case is of an infinite current carrying conductor. What is the exact value of the magnetic field? So as per, if we use the Biot-Savart law, in case of the infinite current carrying conductor, a conductor whose length is unknown, see, the length is not fixed, it is extending to infinity from here and it is extending to infinity from down as well. Is that fine? And there is a current which is I flowing in this conductor, okay? Current I is flowing, fine? If you want to find the magnetic field due to this current carrying conductor, then we have an expression, and the expression is this. This expression has been derived from the previous expression, this expression. This expression. This is the general expression, and it can be used to evaluate magnetic field in any case. So here, when we use it, for this case, the expression that we come up with is this. The magnetic field due to an infinite current carrying conductor is equal to mu naught times the current divided by 2 pi r. Is this fine? And the magnetic field will be measured in Tesla. This is the unit of magnetic field. Is this fine? Okay, so you have mu naught, which is the permeability of the free space. The value is 4 pi 10 to the power -7 Tesla meter per ampere, and the direction of the magnetic field is determined by the right hand rule. So you know the right hand rule now. So if you want to find the magnetic field on the right, what you have to do towards the point of analysis? You use your right hand. Thumb will go along the direction of current. So the magnetic field is, the curling of the fingers is toward into the board. So magnetic field on the right will be cross. Okay? Okay? And the magnetic field for a point which is on the left, it is outward. So the magnetic field here is out. Is this clear? Now, understand. For a point, say for example, this is the conductor. The current is flowing like this. Current is flowing like this. If you want to find the magnetic field at this point, see, this point. So you'll do it like this. So magnetic field is like this. Okay. For a point which is here, like this. Okay. For a point which is here, like this, and for a point which is here, it's coming out. So technically it is forming what? A circular loop, isn't it? If you check the magnetic field here, you will say it is inwards. If you check the magnetic field here, you will say it is like this. If you check the magnetic field here, you will say it is like this, because see, for this point here, it will be outwards. For this point in front, it will be like this. So technically the magnetic field lines, as I told you in the beginning, they are closed curves. They will always be present in the form of circles, in the form of loops, okay? But always closed curves, very important. So this is the expression, and this is the concept of the magnetic field, which is due to an infinite long current carrying wire. This is the expression, and the direction is always found with the help of the right hand rule. Is that fine? Now let us come to a numerical which you are good at solving, and then
What's the formula for?
this formula to calculate the magnetic field for infinite. Now the previous formula that I gave is for anything, any shape, you can use this. See, and it is small, and to find the total you have to integrate. Fine, but here we have already integrated the expression and we have come up with this result, mu naught I divided by 2 pi. Agree, is it clear? The direction, is it clear? Okay, now let us come to the numerical. Example 1. A transmission line string 5 meter above the ground carries a current of 335 amperes. There is a transmission line going on, okay? And it is how much? 5 meter above the ground. Now this is the ground. And the current that it carries is 335 amperes. And the distance from the ground is 5 meters, okay? Do you know you're always you're asked not to go through to a region where there are transmission lines which are carrying huge currents? Not because that these transmission lines will sometimes break and they will give you electrical shock. No. The reason is when you go near these lines, what is happening? Their voltage and their current carrying capacity is much higher. Okay. So therefore, when current flows through these conductors, what is happening? They're generating their own magnetic fields, and when you go near that, your body carries blood, which consists of iron, isn't it? Hemoglobin, which has iron as a central metal atom. You have sodium as well. You have magnesium as well. So these ions respond to the magnetic field. They experience force, which can disturb the metabolism of the body, and you can fall sick. That is why you're advised not to go near the transmission lines. Okay. So the question is, what is the magnitude of the magnetic field on the ground directly below the wire? Directly below the. So there is a wire. The length of the wire is unknown. It has to be because it is a transmission line. So that means it is an infinite current conductor, isn't it? Is that fine? And for an infinite current carrying conductor, we know the expression. You are asked to find the magnetic field directly below the ground. Tell me. What will be the expression? How will you do it? Yeah, of course. That is mu naught times the current upon 2 pi r, isn't it? 4 pi 10 to the power -7 multiplied by the current. What is the current? 335 upon 2 pi is what? We will cancel that. We don't need to put in the value. R is how much? 5. Is that fine? Okay. So pi and pi will cancel. You can use your calculators to find the result. It is 4 times 335 times 10 to the power -8. Because 5 into 2 are 10 in the denominator as well. How much is 4 times 335? Throw us at side. 1340 times 10 to the power -8 Tesla. This is the value. Did you get the same result?
Yes.
Yeah. So you can change it. 1.340 times 10 to the power -5 Tesla. This is the actual result. Fine? Can you tell me the direction for the magnetic field here? What is the direction for the magnetic field on ground? I don't know in which way is the current flowing. It can flow left to right, it can flow right to left. So in this case that I have shown here, what is the direction of the magnetic field on the ground? Yes? In or out? In or out? What is the direction of the magnetic field on the ground? In or out?
You can't do it because it's under.
No. Under. The point is here on the ground. Current is flowing like this, okay? Yeah, it is inwards. If the current was flowing the opposite direction, then it was outwards. Is that fine? You don't have to keep it like this. When you keep it like this, how will you go to the point? Stretch your hands in such a way. Understand? The first step is thumb towards along the direction of current. Second, stretch your hand towards the point. The point is here. Now go cross it. Curl it. When you curl it, it is going in. That is where it's cross. Is that fine? Okay. Next question.
Mr. I don't get how's it going in?
How is it going in? See, the current is flowing like this. The point is here, isn't it? Right? So what you will do? First, your thumb, it will be like this. Thumb along the direction and fingers towards the point of analysis. Okay? Now you have to curl it. When you curl it, it is going in. Isn't it? So that is why the magnetic field here is inwards. Clear? Okay, yes, we got the same result, 1.34 10 to the power negative 5. Okay. Next, come on, do this question. A magnetometer placed 3 cm away from a very long cable wire registers a magnetic field intensity of 0.2 millitesla. We have to find the current in the cable. Come on, tell me. We already have the magnetic field. Distance is also given. We have to find the current. Come on, do it. It is a magnetometer. It measures the magnetic field. Okay. This is a device which detects and finds the direction of the magnetic field. Come on, tell me, how do you solve it? Tell me the answer.
1.3 times 10 to the 3 times 10 to the power negative 8.
Negative 8 for this. Did you change the values? It's 3 centimeter. It is 0.2 millitesla. Standard value is Tesla. So magnetic field is already known. How much is the magnetic field? 0.2 millitesla. Okay. So if you want to change it to Tesla, it is 0.2 times 10 to the power negative 3 Tesla. 30? Okay. Distance is also given. It is 3 centimeters, which is 0.03 meters. Okay. So we are asked to find the current. So magnetic field, as you know the expression. What is the expression? Yes? The expression for the magnetic field. Mu naught times the current upon 2 pi r, right? So we have to find the current. Just use your calculus. Magnetic field is 0.2 10 to the power negative 3 times 2 times pi times 0.03 upon 4 pi 10 to the power negative 7. That is your current. So see, pi and pi will cancel. 2, 4 and this will cancel. So it will be, we have to write here negative 4. So it will be negative 4 and this will also cancel, so it will be negative 3. Yeah, it will be 30. 30 ampere is the correct answer. You solve it with your calculus. I was solving it by cancellation. No? You didn't get it?
No. It's the same, so we got it wrong.
How? I think you are not, you have to use this value and this value. Just show me. You might have done something wrong. 4 pi 2 to the power. It is 0.2. How? You have written 2. 0.2. And in the denominator 2 into.
What is this?
I know what to do.
That's why you know that
This is so easy.
Oh, come on. You are using. You have to find this. So current is equal to magnetic field times 2 pi r upon mu naught. Now put the values. Put the values again. Find me. You will get me the result. You got it?
Yes. Wait, can you go to the?
Yeah, 30 ampere is correct.
Can you go to the other side?
Other slide.
Yeah. No. Yeah.
Khalas?
Yes.
Now, 3 questions. I want this row to solve the first one, this row to solve the second one, and these very good students to solve the third one. Come on. Someone from each row has to come up with answer. If you don't come, I will leave. I will not come from tomorrow. Wallahi. Solve. Second question. It is formula based, nothing else. What are you? She's broken the display.
Yeah.
You're playing with the display? You bring a sandbag and punch the sandbag. Don't punch the.
Mister,
Yeah.
number one.
Yeah? What is the answer?
I didn't do it, mister. I'm gonna do
Solve it, solve it.
Yeah, I will solve.
Hind, what you're discussing the question?
Yes. No, the black computer has something. Eight multiplied by 10 to the power minus 7.
For the third one? What is the answer?
8 multiplied by 10 to the power
8 times 10 to the power
minus 7.
-7. That's it?
Yeah.
How far? Meter, okay?
Yeah.
Okay, good.
Mr. Ours is 1.43.
Yeah.
1.4 what? 43.
That's the power of -8, mister.
-8?
Yeah.
The second one. Hello, you guys. Sarah Basil, Tafla. Sorry. Ali Abdul Majid. You got the answer, Malia? What is the answer? Tell me the answer. One point.
1.2. No. 1.12.
One. Okay, that's fine.
12.5. 125
Okay.
times 10 to the power 5.
Any?
Can check out the
1 point. Okay, good. So she has also got to say. So the first question is, I think, the easiest. The magnetic field strength, distance is given, current is given. You just have to put in the values. So that means the magnetic field in the first case, it is equal to 4 pi 10 to the power -7. Current is given. How much is the current? 0.25, 3.5. Okay, so it is 0.25 divided by, so it is mu naught times the current divided by 2 pi and r. R is 35 or 3.5? 3.5, right? So that is it. You have to find the value. You got it? So this and this will go to 1R to 2R. So it is 5.5. So it is 0.5 upon 3.5 multiplied by 10 to the power -7 Tesla. So this will be the first. How much is it? 0.5 by 3.5? One point something.
No, 0.1. 0.143.
This 0.5 by 3.5?
The entire thing or just 0.1?
Yeah, this.
Yeah, 0.14.
0.14. So it is 1.4 10 to the power -8. This is the first. For the second one, what was the question? For the second one, what was the question? The magnetic field strength produced by a very long current carrying at a distance. So the distance is given, is E, and the value is also given. So what is the current? We have to find the current. 0.5 meter, 0.045. So the magnetic field is 0.045. It will be equal to mu naught 4 pi 10 to the power negative 7 times the current, which is which we have to find, and the distance is 0.5. So current would be I divided by 2 pi times the distance, and the distance is 0.5. Okay? Yeah. Find the value of current for me. Pi will go to 1R to 2R. So this will be 1R, this is 4R. So it is 0.045 upon 4 multiplied by 10 to the power 7. Tell me the value. Just divide this 0.045 by 4. Come on. Yes, Hamda. Do this.
0.0125.
This multiplied by 10 to the power 7. 112,500.
Yes. 112,500.
Is that fine? I think she had got the same result, yeah. And the last one, current already given, magnetic field already given. We have to find the distance. So it is 2 ampere and 0.5 Tesla. For the last question, magnetic field is 0.5. So it will be mu naught, which is 4 pi 10 to the power negative 7 times the current. How much is the current? 2 amperes, right? So it is 2 amperes here divided by 2 pi, and this distance has to be found. So this and this will cancel, 2 and 2 will cancel. So the distance is 4 upon 0.5 times 10 to the power negative 7, and that is 8. You got the same value? Right? You got the same result? Yes. Yeah, that is it. Khalas. So this is the concept of a current carrying conductor which generates its magnetic field. You know the direction and you also know the magnitude. Is that fine? Clear?
Yes.
Any doubt in this? So I will give you a short homework. Yes? Yes, tell me.
Last 7 minutes ago.
But I started 10 minutes late. Why don't you come up with the attendance, man? I'm actually waiting for you.
Seriously?
Yeah, of course.
I was waiting for you.
But where is the attendance, man? In the same?
Yeah.
Okay, stop. So the homework is, if the current is flowing in a circular loop, current is flowing I, the radius is R, what will be the magnetic field, the magnitude of the magnetic field at the center? We have evaluated it for a straight current carrying conductor. Expression was mu naught I divided by 2 pi R. But the question is, the current flows in a loop. What will be the magnetic field? So inshallah we'll do that tomorrow. Is that fine? Khalas. Thank you so much.